We are recording. As again, as last time. Oh, yes, more people. Thank you very much for coming. So yeah, sadly for the people who weren't there last week, I'm very sorry that I forgot to record. So you might be a bit surprised of the fact that I'm not using slides anymore. I'm using
Wait,
notes.
last week there wasn't a thing last week, right? Like you,
Last week I did the same thing of presenting, but using my like notes.
but you said you were busy. Like, do you mean 2 weeks ago?
Sorry, yeah.
Yeah.
Oh God, if I'm starting to forget things again already, this is going to be an issue. But yeah, so the last time, so yeah, not last week, but 2 weeks ago, I already did the recap um, uh, using this format instead of slides, with the argument being that one, it's less work for me, and it arguably, I hope it encourages people to ask more questions, but we'll see about that. Um, but yeah, so this is sort of a change of format to freshen things up a bit. So, but the idea again is to more don't feel free to ask questions during the recap, and we'll discuss exercise. I have not actually done many of the exercise for this week, so we can maybe try them live. Anyway, uh, can I maybe quickly ask if you guys had time to do the reading?
I had a bit of a look, but I didn't have that much.
Yeah, okay, so
I did the reading and several exercises this morning.
okay, great. By the way, I think if you have questions, maybe ask them in the thread. I can so that I don't have to check between the thread and the voice chat. Okay, so 2 weeks ago, then we were talking about um, the basically how to decompose a function when you have a basis or an orthogonal basis, and the sort of the next chapter after that is to um, dig a bit more between these representation, and so there's this nice theorem called the Riesz representation theorem that's actually so the result between the dual space of a Hilbert space and saying that basically the dual space is isomorphic to the primal space, which is generally not true in Banach space. So it's another very nice property that Hilbert space have is that the the dual space is essentially the same. So the starting point is to say, okay, we take a Hilbert space and some vector y in it, construct a map phi of y, which will be linear from the scalar field, which is simply the inner product between x and y. And it's reasonably easy to show that this is just a continuous linear form, so it's in the dual space. So basically two properties to use. So phi of y here is in the dual space, and so what we can say about this is that we can embed the primal in the dual space, and it goes the other way as well. So we can take any phi in the dual space and identify it with some y in H. So to give a like sketch of the proof, we only have one way, we have to show the other way. So we take some arbitrary phi in our dual space, and we want to construct a y. So proof starts us as taking the kernel of phi, so all the vectors that maps to 0. Because this is continuous and the kernel, we know that the kernel has to be a closed subspace. So there are sort of two cases, either y is equal to h. So all of h maps to 0, so the only reasonable choice here is y equals 0. And otherwise we have to manipulate between take the some x in H without y, so x does not map to 0, and because we can take the orthogonal projection, we then decompose x0 two parts with one, so one being this part here that is definitely not 0, and so we can show that phi of x0 has to be non-zero, and actually it has to be equal to phi of the orthogonal projection on the uh, orthogonal complement of the kernel. So this element is what we need essentially to get this the y that we need. So we take x1 as simply being the x minus the. We're essentially taking away the orthogonal complement, and yeah, we just have to apply some scaling factor to get the right norm, but otherwise we have the y that works as intended. And yeah, the only last part is just showing that it's unique, but it's not super hard. And this is basically all the so it's actually a very short section on this theorem, but it's used in the next part. So the next section is about adjoints of bounded operators. So again, all stuff that you might have seen already in finite dimensional linear algebra, where you take some map, so some continuous linear map T between two Hilbert spaces H and K. And the theorem is that we can find a unique T star from K to H that is also continuous and linear, that satisfies that for any H in H and for any K in K, this inner product THK, which is an inner product in K, is equal to this inner product in H, H, and T star of K. So this T star here is called the adjoint operator of T. Adjoint being really this property that you can swap it out in the inner products. So how to construct such an operator? Well, we can fix some k in K and consider the map from H, the inner product T of H and K. So this map here is just a linear functional on H. So it has to be continuous and so on. So we can use this Riesz representation theorem to find a unique vector T star of K. So we'll call it T star of K, such that this phi of K here is just H star of K, or which H times K. So we can find our T star of K, and this essentially lets us define a map T star from K to H. And yeah, the sort of the remainder of the proof is just showing that T star is linear and bounded, and that its norm is under the norm of T. Again, I think I've heard a few people coming in. Don't hesitate to interrupt for questions. So to give some easy examples of adjoint operators, well, if you have a finite dimensional matrix, then it's the transpose or the complex conjugate. So take H equal the complex number, so Cn k equals Cm, then it's equivalent to or represented by a matrix A with m rows and n columns. So its transpose is just the matrix transpose. Transpose the matrix and take the complex conjugate of every element. But for another example is on directly L2. So remember, L2 is sort of the mother of all Hilbert spaces. So we take L2 and take a map from L2 to L2, R being the right shift operator. So what it does is simply shifts a sequence one to the right and puts a 0 at the beginning. So if you want to find the adjoint of this operator, well, you want to apply it for some h and k and find this expression for the sum. So it's pretty easy to show that this is equivalent to saying, okay, it's same thing as the inner product of H with L, K, where L is the left shift operator. So we have that that. So we have that the adjoint of the right shift operator is the left shift operator, and similarly the adjoint of the left shift operator is simply the right shift operator. And so in the section they sort of introduce it that way, and as okay, a property is this package operator, but it's true in general. So the adjoint of the adjoint is the same as where we started. So a few properties about adjoint operators. So we have some two Hilbert spaces and TNS, continuous linear operators, and the adjoint of the adjoint is the original operator. The norm of the adjoint is the same as the norm of the original operator. We have some properties for the multiplication by scalar and addition of two operators. And note that this, because we have the orthogonal complement here, this means that taking the adjoint is not strictly a linear operation, because any scalar multiplication is mapped to the complex conjugate if we have complex numbers, so it's not strictly linear. And otherwise, another nice property is that again, exactly the same as it works for matrices. If you have the composition of few operators, then the adjoint of T2, T1 is equals to the adjoint of T1 and times the adjoint of T2. And yeah, the last corollary is about okay, how this works with the inverse. So all this stuff you should know from linear algebra, but it still works again in infinite dimensional Hibble spaces. They have some other properties relating to the geometry of these operators. So the nice theorem is about if we take the kernel of our operator C, then is the orthogonal complement of the range of T star, and then the closure of the range of T. Note that we have to take the closure here because it's not necessarily closed, whereas we know that the kernel is closed, so its orthogonal complement is also closed. So the closure of the range of T is equal to the orthogonal complement of the kernel of T star. So almost the final theorem is about sort of going back to an example that we saw with the orthogonal projection. We saw that it's self-adjoint, so you can have these operators from the same space, one space to the same, that are their own adjoints, and so these are called self-adjoint operators. And they're actually fairly important in functional analysis, but specifically for PDEs and for spectral analysis, because if you have a self-adjoint operator, you can say things that are essentially the equivalent of a symmetric or Hermitian matrix in linear algebra. So you can have some pretty nice things to say about its eigenvalues and even eigenvectors in some cases. Particularly for a certain class of operators that are self-adjoint, but also have some other properties. Those are the operators that you can find, for which you can find a countable number of eigenvalues, each with eigenvectors. You have an orthogonal basis of eigenvectors. But yeah, so a self-adjoint operator is simply an operator that is its own adjoint. And to give a sort of nice example that is not in the book actually, we take the operator, so the second derivative, say L2, but always take the continuous functions. We claim that this operator is self-adjoint on L2, but we have to fix the domain. So the domain of this operator has to be, well, it has to be the function that are at least twice differentiable. Here we're taking actually the infinitely differentiable functions, and we have to put some boundary conditions. So this is something that's very common in PDEs. So in PDEs, if you want to solve a PDE, you have an initial condition, but you also have to input some boundary conditions. And so in this case, we say that our function have to be 0 at both endpoints. So if you do some calculations, you find that indeed, basically you just have to apply integration by parts once, and then you can make appear your f and g, and so the right terms in your integral disappear, and so indeed the inner product f and tg is the same as tf and g. And so this operator is indeed self-adjoint, and sort of coming back to the point about the spectral theory, the spectrum of this operator is given by essentially the Fourier basis. So the eigenvectors are the Fourier functions, and the coefficient is sort of linked to that. It's one of the reasons why this is a nice operator, because even though it's unbounded, right, the differential operator are not bounded, but you can still analyze it spectrally. So yeah, time for questions and or exercises. So as I mentioned to the people in the beginning, there's a few exercises, and I have not actually done all of them, even though I recommended a few, so I have time, so I can do them live. Any questions?
Nothing from me at the moment.
Did you, let's see which exercise I recommended. So I think 4.24 is kind of optional, but we can look at the 4.35, 36, and 37. Find them. Yeah, those are nice. Actually, in my notes for the exercises. For the 4.35, I have to show that idempotent self-adjoints are orthogonal projections. If you have any questions, feel free to ask them anytime. But have H this. P be a continuous operator on H. That P squared equals P equal P star. Prove that range of P has to be closed. And that P is the same as the projection on its range.
Right, so this is one that I attempted. I didn't figure out the key object that you're supposed to look at to try to solve this, so I looked at the answer. So I know what the object is. I'm curious, sort of, if you've attempted this one, whether
I have not,
it was
so
obvious to you. Okay.
I'm thinking about it. I think the range thing, you have to use the properties of the between the probably something like this.
I looked at using those. Um, it doesn't. It didn't seem to me that that gets you very far because you can obviously get rid of the adjoints in both of these expressions because your operator is self-adjoint, but you still can kind of only get from a closed set to. So if I just sort of apply both of these, I get the kernel of P is the orthogonal complement of the range of P, and then the closure of the range of P is the orthogonal complement of the kernel of P, which is the complement of the range of P. Um,
Yeah, so as a quick
I,
vocabulary
yeah,
question, the range is the set of values that are attained by the operator, right? Something is in
yes,
range, you can find an input that gets mapped to that.
yeah.
Because I think we might be able to use the like the p squared thing to say that like to make something appear and disappear in a like if you have some product p squared xy, there it is p of x bar, but it's also p of x times p of y maybe.
Yes,
Um,
you've written a true expression.
yeah, we'll see where it gets us. Maybe let's see if I can copy things across documents. Oh, I cannot. Be better if I seems to work. Okay, so think about this. Pull up the chat. Questions I see are not. How will we find this? Maybe we would just have to pull out the like the sequential definition of closed.
That might work. I don't know if I want to hint too much, but that's the solution in the book doesn't do that.
Uh-huh. And is the so maybe without telling, is the solution in the book very long, or does it use a clever trick? Because otherwise, you might be here a
Uh,
while.
it does use. Well, I have no idea how clever the trick is. I didn't come up with it myself, so I can't really gauge. But you can look at the range of P as the kernel of something else.
Uh-huh. Is it? Oh, maybe it has to be something like the to ah like maybe I minus p would be the right one, right?
That makes sense in the context of projections. Yes,
Yeah.
that's
Maybe
basically P, you know,
yeah,
the
because
projection onto Y complement.
yeah, so in that case the uh I minus p will have the kernel the same as the range. unless I'm
Yeah, so the first part of the book solution is basically showing that.
find that should be. Actually, I think that might be in the properties of the. Of these orthogonal complements, but again, we don't know that it's orthogonal in this case, so you have to think about it. Yeah, I think we might get away then with using this. Right, if you find
Are you just deep in thought, or has the stream
yeah,
frozen?
I'm just thinking. Um, yeah, I'm not used to do these things, so that kind of stuff live. So it's my performance may be suboptimal. Just say. Um, yeah, it's surprisingly difficult. Yeah, if anyone has any ideas or other questions. Otherwise, if we like, because I still want to do this on my own. So if we spend too much time, maybe we should move on to
Yeah,
another one.
I think that's a good idea.
Yeah, maybe
Oh,
because
We can always circle back later. Like, next week maybe.
yeah, but so on that topic, maybe so I definitely don't have time to like prepare all the stuff every week, but one thing that might be nice might be okay. One week we read new material, and the next week we sort of do exercises. I think that might be a sort of nice way to not spending every two meet up only every 2 weeks. Well,
yeah, if that's better for you, then I think that's perfectly fine.
also
You're
because
running the show in terms of the materials.
yeah, but even then, like I think the exercises are really the meat of the book. So
Yes.
it's nice if we can do more.
Yeah.
Do 4.36 instead. So we have an operator T here bounded, and it's called Q adjoint. If T equal minus T star, so the equivalent of an anti-symmetric operator. So yeah, here the goal is to show every operator can be written as a sum of a self-adjoint and skew-adjoint. Remember, so if you think of the finite dimensional case, it's pretty easy. What point is there's a unique way to write this? Sum
Yeah.
joint. So I already have an idea, but maybe I'll let people think about it. It really helps in this case to think about how you would do this in the finite dimensional case. and replace. And in the finite dimensional case, you just have to replace self-adjoint with symmetric or Hermitian, and then skew adjoint with anti-symmetric or anti-Hermitian. Particularly, let's think maybe, okay, we have some t that's linear and bounded, and it might not be the case that it's self-adjoint or skew adjoint, but you can always take its adjoint. So one of the ways
so
you might do. Yeah.
I was just gonna say this reminds me of a question that an exercise that I think we did last week.
Yeah, with
on
the
even and odd functions.
Yeah, it's very.
And I think it's exactly the same trick.
Yeah, it's exactly the same trick. So if you want to give it.
Sure. So you take the self-adjoint part is 1/2 t plus t star, and the skew adjoint half is 1/2 t minus t star. And it's pretty simple to show that those are indeed self-adjoint and skew adjoint respectively. Just take the adjoint and you get either the same thing or minus the same thing once you work out the algebra. And if you add them together, you get the original operator back.
Let's see. We have to take the. Yeah, I think we have to take the divided by half in this case too.
Yes.
It's as you said, exactly the same trick as the even and odd function. So maybe there's some more general property here. But yeah, we take the t plus t star and divide it by 2, and it's an adjoint, and t minus t star is q. So star minus.
And I think I actually skipped the part where you show uniqueness.
Yeah, how would you show? So I guess you would suppose that there is like another way to write it.
If I have like t equals a plus s, and I also have t equals a prime plus s prime, then maybe I can, I don't know, figure out that a equals a prime somehow.
Yeah, so take a plus s and prime plus s prime, and we know already that so a and a prime are self-adjoint, and s prime are q-adjoint. So maybe one trick we can do is means that a minus a prime equal to s prime minus a. I think then like I don't think they showed that it's easy to show that the sum of two self-adjoint operators has to be self-adjoint.
Right, and then that is skew self-adjoint, which implies that I think if it's both self-adjoint and skew adjoint, then it's 0.
Yeah, so this has to be 0. So basically, yeah, we have an operator that's both self-adjoint and skew adjoint, so it has to be 0. Equals a prime s equals s prime. Okay. That wasn't too bad. Um, yeah, maybe let's do the 37 because it looks nice actually. I think after that, I mean the next ones are still about self-adjoint, but then, as mentioned, then it really goes down into the vector theory stuff. So yeah, I think we might do the 37 and then call it a day, mostly because I'm supposed to wake up very early tomorrow, so I probably should get some
That
sleep.
works for me.
Okay, so 4.37. We have some the n bounded sequence, and we take the operator CL on
So
the
this is our familiar diagonal operator.
yeah, we've seen it a few. Although here in actually it's a bounded sequence, so it's not even an element of value, but yes, because it's bounded, it works. Lambda times right nicely find determine adjoint of that. This might be too easy actually, but it's fine.
Yeah, I think my answer here was about 4 lines.
Yeah, so I think it should be obvious to everyone that we might at least try like candidate times we take all the lambdas and take the complex conjugate.
Which is exactly the same thing you would do if you were looking at a finite diagonal operator.
Yeah,
Finite
exactly.
dimensional, I mean.
If you want maybe to use the definition x b in L2, and so we find have this lambda y that has to be sum of lambda n
You have lambda k xk times yk conjugate.
k is here. B conjugate. Interestingly, here we have to
I can basically move the lambda k over,
yeah
and if I have lambda k conjugate times, or sorry, lambda k times yk conjugate, that is in brackets lambda k times yk end bracket conjugate.
yeah. So because the conjugate applies twice. Yeah, pretty trivial. Doesn't write nonsense. So yeah, the this works as intended.
Mm-hmm.
Yeah, not the most difficult one. Sorry. Yeah, I think maybe so because I unfortunately don't have too much time to stick around to that today. I propose to maybe like next week I know next week is supposed to be nearing the Thanksgiving, right?
Thanksgiving is the week after next.
Okay,
But
so anyway,
yeah, depending on when you want to
I
schedule the
mean
next meeting.
it's still it's still good for me on Sunday, but yeah, so I suggest
Yeah.
that next week we have meeting but only for exercises, but then it might be nice to prepare the exercise. So yeah, I think that might be something to try. Does anyone have any questions, comments, or anything else to say before we leave for tonight? Maybe if I can ask one question. So I asked it last time. What do people who weren't there last time think about the new format of instead of me using slides, instead having these handwritten notes? Okay, yes. I guess no one has any comments.
Yeah, I was there last time, and I think I already gave my comments.
Yeah, and I heard them. So okay, then let's leave it at that. Thank you very much for coming, and then we'll meet again next week, but just for exercises. See you then.
All right, thanks for hosting.
Yeah, bye.